So the last thing we're going to learn about circuits is the role of batteries and how to understand the chemical properties of batteries, and another term, the electromotive force and the property of internal resistance. As a battery gets used up over time, it actually has resistance inside of it that steals some of the energy of the battery. So in this little video, we're going to learn how to calculate that internal resistance and use the term EMF, electromotive force, and really understand how batteries work. Okay, so the objectives here are to define what electromotive force of a battery is, distinguish between the electromotive force and the actual potential that we see when we plug it into a voltmeter, and understand the presence of internal resistance in battery and how it changes as it's being used. And finally, to design an experiment to actually measure that internal resistance. This is often an IA experiment for an SL student. All right, so what is the electromotive force? Well, electromotive force is what you would read on the package of a battery. If you buy a battery, let's say a 9-volt or a 12-volt battery or a 1.5-volt battery, what you're reading is the electromotive force. And the electromotive force is actually the work done by the chemical reaction to move a charge from one terminal to another. Okay, so it's the work done per unit of charge to move the charge from one terminal to the other, and it's measured in volts. Volts is measured in joules per coulomb. That's work done per unit charge. All right, so that's your electromotive force. And your battery would say, for example, a 9-volt battery would be 9 joules per coulomb of charge. That's how much work a 9-volt battery EMF would be using up. Okay, so the EMF in this battery is the work done to move that charge. Okay, but if I plugged in a voltmeter on the outside, it wouldn't read 9 volts. It would read something like 8.9 volts. Okay, so that's always strange. You plug in the voltmeter on the ends of the battery, and it's giving you less voltage than what you paid for. So what's going on? Where did that extra 0.1 volts go? Well, it's going to do work against internal resistance of a battery. So often voltmeters connected outside of the battery do not read the true EMF. Okay, they read the actual potential that's remaining to move a charge in the external part of the circuit. And so some energy is used by the chemical reaction to overcome internal resistance. The chemical reaction has to overcome some type of properties inside of the battery to move the charge from one side to the other. Okay, and what's actually happening is in a chemical battery, you have ions. You have salts that are moving inside of the battery to balance the charges. And they have electrostatic attraction and repulsion, and they provide the resistance. Okay, so certain salts have less resistance than other. Okay, and as the battery gets used up, these salts have a harder time migrating to balance the charges. Okay, and create those potentials. So that's where the internal resistance comes from. Okay, in order for us to measure internal resistance of a battery, we need to put it in a circuit. So here's a battery that I've drawn that has your cell structure, negative, low potential, high potential, and your internal resistance inside of the battery, marked by little r, connected to a circuit. You got an ammeter in the circuit, and you have a resistor that you can measure the voltage or the load across it. And this voltage would be my external potential that's provided by the battery. Okay, so the formula that I have here explains how EMF can be calculated. EMF, remember, is the actual work that chemical reaction has available to it. So the EMF of a battery, let's say the battery is a 9-volt battery, okay, that EMF is equal to the work that charge can do outside of the battery, which is IR. Okay, so remember, Ohm's law says V equals IR. So this voltage on the outside is the work done by that charge outside of the battery, I capital R, plus the work done by the charge inside of the battery. The current is going to be the same inside of the battery times little r, which is the resistor inside. So V inside the battery is equal to I times little r. And that little r, that little r is my internal resistance. Okay, so if I would add that up, current times the resistor on the outside plus current times the resistor on the inside, that should all add up to 9 volts. So like I said in the other problem, if I measured 8.9 volts here, okay, Okay, so I plugged in a fresh battery and I measured 8.9 volts there. That must mean that I have 0.1 volts of energy per coulomb being used up inside of the battery. So as long as I know the current, I'll be able to solve for the internal resistance of that battery. So let's see if we can do that in practice. Let's calculate the internal resistance of a 9-volt battery when the potential difference across the component R is 8.6. So let's look at it when it's 8.6 and the current measures 1. So let's delete this. Let's get rid of that. Okay. Let's make the current here 1 ampere. Let's make the voltage being measured outside the circuit 8.6 volts. Okay. So remember, that's 8.6 volts plus 1.0 ampere times R. All right. So how would I solve this? 9 volts minus 8.6 volts is equal to 1.0 amperes times R. All right, and then if I just move this over here, you will see that 0.4 volts divided by 1.0 amperes is equal to R. So my internal resistance is 0.4 ohms is equal to my internal resistance. And that's roughly what it would be. It can't be a large resistance. Usually, like a really dead battery, the internal resistance would be something like 2 ohms. It's not a lot, but it's still enough when I have high currents to start stealing some voltage. So we notice internal resistance a lot when the currents are huge. Okay, the larger the current, the more energy is going to be lost inside of that battery. That's something to keep in mind. Okay, so how would we determine the internal resistance from an actual experiment? So if you're going to do this for an IA, it's pretty well the same thing. What you need to do, we can't just do a single measurement like we did right here. I can't just plug it into one resistor and get a measurement. There'd be a lot of error in that. So remember, in IAs and lab experiments, we want to create a graph, some type of graphical relationship between this. So what we would do is we'd create a circuit with a battery. And remember, this component, that is a variable resistor. Okay, so I can change the resistance, let's say from like 10 ohms all the way up to 1,000 ohms. I can then vary the resistance. If I vary the resistance in here, I will change the current. Okay, so knowing that, I can create a graph where I measure the external voltage. Okay, what happens to my external voltage when I change the current? Because I'm changing that internal resistor. So if I plotted my external voltage, I, capital R, versus my current, it would give me a straight line. Okay, that's interesting. It gives me a straight line, and this y-intercept would mean something. Okay, and this slope would also mean something. So let's try to see what that means. If I take a look at this linearized equation, all I'm using is the equation that said, let's find that green color. I'm using the equation that said EMF is equal to IR plus I little r. Okay, remember this is the voltage, external voltage, and this is the internal energy lost, and that's the EMF. So if I rearrange that so that this becomes my Y variable, okay, then I would see that EMF minus I little r is equal to IR, okay, which is my voltage external, okay? So, and that's what I have right over here. So my Y variable in that graph, and you can pause and go back and see if you want. My Y variable is the external voltage, okay? My intercept, my Y-intercept is going to be my EMF of the battery, okay? My slope is, this is my X variable. The current is my X variable. So my slope is my internal resistance. So slope is internal resistance. Okay? So if some of you are having a hard time with your IA right now, you can then change to something like this, where you would look at how does a variable affect the internal resistance of a chemical battery. You might want to try to check that out. That's a nice SL IA if you're very stuck right now. Okay, so again, in the experiment, you would have a variable resistor that you can change its resistance, which would then change the current. If I change the current, okay, that would be my x-axis, that would be my independent variable, and I would measure how that affects the external voltage. Okay, and according to this linearized equation, if I plot my external voltage over top of the current, I will get a y-intercept, that is the EMF of the battery, and R, which would be the internal resistance. The slope of that graph is going to be my internal resistance. And that's pretty well it for batteries.